In this video, we will discuss units. To begin, we will explore why units are important for calculating and reporting values. Then we will look at the SI units. Finally, we will cover unit combinations, substitutions, and go through the basic methodology of how we can balance units.
So when we report our values, we should be mindful to include our units. So where, for example, a quantity represents a physical quantity, we must always include the associated unit of measurement for that physical quantity. And so let's take the counter example to understand why it's important to write the unit down. Not writing a unit can lead to ambiguity. So for example, if I were to present the number 5, well, the question is 5 what? Is it 5 meters or 5 seconds? And these are two completely different physical quantities. They represent a unit of measurement that indicates a completely separate physical quantity. And that's not the only two units of measurement. We could have 5 centimeters, 5 kilograms, 5 British thermal units, 5 meters per second, 5 per meter seconds, 5 kilometers. Now, these are all completely different physical quantities that may be measured directly or calculated. Nevertheless, the units are vital. So let's take the example of the Mars Climate Orbiter as a real-life example that really indicates how important units are. So in the Mars Climate Orbiter Mishap Investigation Board's investigation of the Mars Climate Orbiter, they had this to say in their final documentation. The Mars Climate Orbiter Mishap Investigation Board has determined that the root cause for the loss of the MCO spacecraft was the failure to use metric units in the coding of a ground software file, small forces, used in the trajectory models. Specifically, thruster performance data in English units instead of metric units was used in the software. Application code titled SM Forces. Now, here we see a clear example where a lack of congruity between the two units has led to a mission failure for NASA. So this is a clear example of why units are vital. Other examples, so let's think about units of measurements. There we just had an example of two competing units of measurements, that they are meant to represent the same physical quantity, but the unit of measurement is different. So for example, unit of measurement, when we're talking about length, what comes to mind? We might think, a meter, we might think, feet. It really depends on the context. So if we decide to go and visit a local furniture store, they might report all their measurements in centimeters. But when we're talking about humans, generally speaking, we tend to consider feet and inches to represent their height. But again, contextually, if you're outside of the UK, you might also report human height as centimeters as well. And another example, what about weight? So if you're based in the UK, if you're talking about the weight of a baby, for example, often people will report this as pounds and ounces, whereas if you're talking about an adult, it will be usually reported in stones. Now, in many European countries, the standardization is to talk about the measurements as kilograms. And this is getting to our crescendo, is that generally speaking, the Europeans have the right. That leads us to the notion of SI units. So normally in engineering, we will present units in quantities that correspond to the international system units. So a key skill here is to be able to convert between SI units and imperial or other conventions. So we've already talked about how some of these units of measurements are almost like legacy units of measurements that we're slowly weaning ourselves off. But the key thing is being able to convert from one unit of measurement to another unit of measurement. And here we have the 5 physical properties that the SI units define and from which all other units are derived from. So, we have length, which is measured in the units of meters. We have, and that's given the abbreviation of M, mass, unit of kilogram, kg, time, seconds, given the unit of S or the abbreviation of S, temperature, Kelvin, abbreviation K, and amount of substance, mole, given the abbreviation MOL or mole. Another consideration that is made in the SI units is that of unit prefixes. Now, we can attach prefixes to any unit, so be that grams, be that meters, be that seconds. We can attach these prefixes to those units to actually allow us to talk about the same physical unit, physical quantity with the same unit of measurement, but at completely different scales. So for example, if we were going to compare the weight of an apple compared to that of a sun, we need to have some form of being able to level the playing field so that we can still talk about grams, but the scale of the grams will be quite different. So, generally the factors that are represented by these unit prefixes. So we have nano, which represents 10 to the minus 9, and we usually put a symbol n in front of our units. And another example is the kilo. So 10 to the power 3, which is 1,000, that is representative of a kilo, and that is given the symbol in front of the unit of K. Now, just note that the convention is to show mass in multiples of kilograms. So otherwise, the base unit, if you will, is 10 to the power 0, which you can see there's no option for 10 to the power 0 between these 2 points here. And that's because that would just be the base unit. So the base unit for length is meters, as we've just seen. Base unit for time, for example, is seconds. So we wouldn't choose to, refer to those as, kilometers as the standard unit of length, as we do for kilograms. So unit substitutions. Now, how do we go about actually approaching more complicated calculated units? So some SI units are actually combination of base units. So those base units we discussed earlier, they can give us or give rise to other more complex units. So for example, we've got force, which is measured in the unit of newtons. Now, newtons is the SI standard for force. Nevertheless, it is based on the base units that we've discussed. So all our units will always reduce down to a form of the base units. So newtons, for example, are simply kilogram meters per second squared. Energy, measured in joule, is a kilogram meter squared per second squared. And pascals, or the measurement of pressure, is kilograms per meters second squared. So these are all three different, these are combination examples of base units that form an SI unit for a different physical quantity. So remembering these combined units. So there's actually kind of a very nice way to remember these, because you might think, okay, I could probably remember that pressure is pascals, but how will I ever remember that the base unit is kilograms per meters second squared? So let's actually think about that. We can use simple equations to remember each of these. All we need to know is the relationship or a relationship of the physical quantities that actually help us to determine the units. So for example, when we're talking about force, well, we know that the equation for force is mass times acceleration. If that's the case, then the units of force is newtons, and the unit of mass and acceleration, well, mass is measured in kilograms, acceleration is meters per second squared. So very quickly we've developed we've got a representation of the base units for the Newton. We can do a similar thing for energy by taking any of the energy equations. I've taken the example of kinetic energy, which has given us, when we plug in our base units, a value of kilogram meter squared per second squared, as we showed earlier. And similarly, Pascal's pressure, well, pressure is just force divided by area. Plugging in our units for both of those, we obtain, and you'll see that now we're using a force, so we'll actually use the unit of newtons, but the base units are kilogram meters per second squared. Now dividing that by an area, which will be meter squared, well, dividing this whole Newton base unit form of the Newton by meter squared, well, one of the meters will cancel out, and then you have a meter at the bottom, and hence you get this equation here. So knowing how to balance units is really important, and knowing how to convert units is really important too. Sometimes, we might be given data sets where the units are all in various systems of units, and what we need to be able to do is be comfortable with going from one system of units to another system of units. And that's really important if you're working in a global company or a global engineering firm or whatever you find yourself in. If sometimes there'll be different locations, and for that different conventions associated with certain units. So we must make sure that when we're doing calculations, that there's consistency within that calculation. Algebra can really help us to convert from one unit to another, and we really must note here that we can only add like units. We can multiply, and there's some rules to multiplication, but really here the problem is that we need to make sure that we can only add like units, okay? So let's take an example. Adding units. Well, if we choose to, a trivial example is add an apple and an orange, well, that just doesn't work, does it? We are not able to present an equation. We're not able to fill out the right-hand side. And this is the same as if we decided to get 100 meters and add 65 seconds to that. Now, what is that going to give us? Is that going to give us anything? Well, it's not going to give us anything meaningful. So what we need to do is we need to make sure that that seconds is actually also meters. And if that's meters, then we can go ahead and add those two together. So here's a basic form of balancing units. So here we have the same unit, 100 kilograms. So we know we're talking about the same physical property, 100 kilograms adding 320 pounds to 100 kilograms. How will we do this? So what we do here is we multiply our pounds by a conversion factor. So every kilogram is actually associated with 2.205 pounds. And what we're going to do here is we'll take our conversion factor and we'll multiply such that we are left with a consistent unit at the end. So if we multiply the pounds by 1 kilogram divided by 2.205 pounds, well, the pounds will cancel out using our knowledge of algebra. And what we'll be left with is the unit of kilograms. And that gives us 100 kilograms plus 145.1 kilograms, which gives us 245.1 kilograms in total.
Thank you for watching this video. In this video, we have looked at the importance of units for calculating and reporting values, explored the SI units, and talked about unit combinations or substitutions, and finally, we looked at how we can balance units.